Hi guys, today's Leet-code problem is climbing stairs. And this is an easy problem if you know recursion and DP here. Like you have to know recursion uh, for solving this problem, okay? And the DP will be the optimal solution here, okay? So that dynamic programming, DP means dynamic programming here. The dynamic programming will be the optimal solution here. So if you want to master recursion, these kind of problems are most important. Okay. So you have to solve these kind of problems to build the logic building in recursion. Okay. So how to get the logic building, like how to get the track of recursion, you will be you will get in eventually when you solve these kind of problems. Okay. So the basically when we will be straight away diving into the problem. Okay. And now we will let us see what's a problem statement is see. Okay. And you are giving a you are climbing a staircase. Okay. You are climbing a staircase. It takes n steps to reach the top. Okay. It takes basically you are at an initial position ground level, and from ground level to reach the top it takes n steps. Okay. Okay, each time you can either climb one or two steps. You can climb one step initially, or else you can climb two steps initially. Okay. In how many distinct ways can you climb to the top? Okay, so the question is, like, in how many ways, like if you climb one step further, one step initially, and you take two steps, two steps again, and you can take one step and two steps, one, two, like this, and you have reached the top. And if you take two steps and one step, one step, one step, two steps, one step, these are the distinct ways to reach the top, right? Like how many, in how many these kind of ways you take to reach the top. Okay. In how many ways, like how many distinct paths you will like for example, uh, um, to reach your destination, like to reach your home, there are n paths, right? Okay. In n paths have subpaths also, right? So in how many paths there, how many from one position to your home position, how many paths are there to reach the home? Okay. How many paths are there to reach the home? Same like this, same kind of question only. This kind of question only, like there is an initial position and the top position. You can reach either one step further or two steps further. In this way, how many ways you can go to the top? Okay. So this is the problem statement here. So we'll try to analyze this problem using recursive tree. Okay. And coming to the recursive tree here. So this is the recursive tree here. And okay. So this is the recursive tree. So from you are starting at this position only. Okay. I have taken for n is equals to 4 here. Okay. So you are at a position 0 comma m, that is initial position. From this position you can go either one position or two positions, right? Okay. First of all, I will go with one position. Okay. So I have I went with one position. Okay. So I will also, so I've reached one position here. Okay. So from one position, I can go either further one position or further two positions, right? So first of all, I will go with one position only further. Okay, from one I will go to two. One plus one will be two, right? So I'll go to two. From here also I can go to plus one position or plus two positions, right? So first I will go with the plus one position. Okay, so I have reached plus one position. I have reached three here. Okay, so from 3, I can either go plus one position or plus two positions. There are two choices, right, for me. So I will go with one position only initially, and from here I will go one position. So I've reached top. That is n is equals to 4. So if at all I am at the if I is my position, if I am at my I is equals to n, that is equal to when I am at I position, top position, then I need to return 1 in that case, because I've reached the top by using these kind of paths in my way. Okay, what type of path you have used here? One, 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 and one. All single ones you have used this path, right? So we will write this problem here. So by using these kind of steps you have reached the path. Okay, and from here I will be returning 1 here. Okay, so I will return 1 here. So I will go two positions here. From here I've rent one position, right? From here I will go two positions now. So I will reach two positions. Okay, so but I'm greater than 5 from I can oh, so I have reached the position where it is greater than top. So in that case I need to return 0, right? So I have reached the position where I cannot go to the top anyway. Like I have the only way I can go is I have to do the -1. But here the cases are I have to go either +1 or +2 positions, not -1, right? So uh, so in this case it is impossible to reach the top, right? So so we have to return 0 here. So okay, 0. So from 3, in how many positions you have reached the top? That will be uh, calculated using how many in how many ways have reached the top by using one step, and how many ways have reached the top by using two steps. That is this thing. So this will be, if we add these two steps, then I will get the answer for 3. That is, in how many ways I have reached the top. Okay, from 3 I have reached the top using one step one time and two steps 0 times. So 1 plus 0 is 1 time. So I will return 0 here, 1 here. Okay, so in how many ways? In one way I have reached the top from 3. Okay, from 3 I have reached the top using by only one way. Okay, so from 2 uh, from 2, how many ways you can reach the top by using one step? Okay, if I go one step from 2, then I'll be returning 1 only, right? So in one way I can reach the top by using one step from 2. Okay, so the same question we have to ask for the two steps also, right? In how many ways you can reach the top by using two steps? Okay, from here we need to use two steps here. Okay, so two steps I have used and I have reached the top here. Okay, my position is equal to top, then I can return 1, right? So I have written 1. So from here, in how many ways you can reach the top by using one step and two step? That will be the sum of one step and two steps, right? So I can reach the top by using one step one time, plus I can reach the top by using two step one time. So 1 plus 1 will be 2. So I can reach the top from 2 in two times, right? Two ways, right? So this is also a valid case. So I need to even uh, so I need to uh, even write this path, right? Uh, so even I need to write this part in how many ways? One, one, and two, right? One, one, and two. This is the position. Okay. So from two, I can reach the top in two distinct ways, right? In two distinct ways. So I have written two ways. So from one, in how many ways I can return to the top by using one step? That is, I can by using one step I can reach the top in two distinct ways from one. Okay, same question we have to ask for two positions also, two steps also. In how many ways I can reach the top by using two steps? Okay, I have to call this function for two. From two steps, how many ways we have to call? So I have to call the other another function, same for the function another time. Okay, this will give me the answer. Okay, so from here I will again uh, call the function for one step from 3. From one step, if I go further one step, how many distinct ways I can reach? Okay, I will call this function and my position is equal to 1 n. So from here I will return 1. So if I call another function, in how many ways I can reach the top? In two ways. Okay, in two steps. So I'll again call this function, it will return 0, then this summation will be equal to 1. So from 1 I can reach the top by using one step two times and plus by using two steps one time. So the summation will be 3. From 1, I can reach the top in, how many ways? 3 distinct ways. So I need to even return this way, right? So in how many ways I can return? So one position, 1, 2, 1, 1, 2, 1. In this path, I can reach the way, right? So from 0, if I use only one step, I can reach the top in 3 distinct ways. Okay, in 3 distinct ways, I can reach the top by using one step. So if you observe here, so my first step will always be 1 here. So from if I initially started with 2 steps, in how many ways I can reach the top? Okay, this is the question. So we will go 2 steps further. So I'll reach 2 here. Okay, from 2 I can go 1 step or 2 steps, right? If I go 1 step, how many ways I can reach? So I will go to 3. From 3 I can go either 1 step or 2 steps, right? If I go 1 step, and how many ways I can reach? So if I go 1 step here, I will reach 4. So I have to return 1, right? So I'll be returning 1 here. From 3 I can go 2 steps, right? From If I go 2 steps, I'll be reaching the position where I can't go to the top, so I'll return 0 here. So if I do the sum of these two, then the answer will be, in one way I can reach the top by using 1 step and 2 steps. Okay, so the so if I draw the path here, so I can go first. Initially I'll be going to 2 steps and 1 step and 1 step. This is the path here. Okay, so from 2, in how many, in one way, in one distinct way I can reach the top from 2. Okay, um, from 2, if I go 2 steps, and how many ways I can reach the top? If I go 2 steps, I'll be reaching the top position, so I will be returning directly 1 here. So from 2, if I go 2 steps further, then I can, in one way I can reach the top. So here, from one way, from 1 step I can reach the top in 1 way. From 2 steps I can reach the top in 1 way. So the both of the summation will be the answer for 0 comma, from 0 comma n, in how many ways I can reach the top if I use 2 steps. Okay, so if this is the solution, 2 and 2, 2 comma 2, right? This is the way. So in how many ways I can reach the top by using 1 step and 2 steps? So from 1 step I can reach the top in 3 ways, and from 2 steps I can reach the top in 2 ways. So in 5 ways I can reach the top from 0. So the overall answer will be 5. So the paths are these only, right? In 1 comma 1 comma 1, 1 comma 1 comma 2, 1 comma 2 comma 1, 2 comma 1 comma 1, 2 comma 2. These are the distinct ways I can reach the top. So this is the solution. We'll try to code this up. So I have to call a function where it will return the solution, right? So I'll call a recursive function, and my initial position will be 0, and this will be n. Okay, public and recur int I comma int n. Okay, so what are the base conditions? If my position is equal to n, then I need to return 1 here. If my position is greater than n, then I need to return 0. This is an impossible case, right? So from here I can go 1 step, right? If I go 1 step, then I need to call for function recur I plus 1, and from here I can go 2 steps, right? 2 steps recur I plus 2 comma 2. So what will be the solution of this? This will be the solution if I return 1 step plus 2 step. This is the problem here. If you try to run this, okay, 2 steps. So here it will be steps here. Okay, and if I try to run this, so it is accepted, right? So for 3 also it is. So we will use our own test case here. So for 4, in 4, how many ways it can go, right? So we have visualized the tree, right? In 4, how many ways it can go? So for 4, it can go 5 times. Okay, in 5 distinct ways it can go. It can reach the top. If we try to submit it, it can give TLE, or else it can accept the solution based on the compiler. Okay, so it is giving TLE for me. So we need to optimize the solution. Okay, in optimization, what we need to observe? So we will observe the uh, we will observe this tree. Okay, now how to optimize the solution? If you carefully observe this tree, okay, if you carefully observe this tree, so see, uh, from here you are going one step, right? From here you are again going one step, and from here you are going two steps. From here I'm going one step, right? So you have reached three here. Okay, from three you have reached again four, right? Okay, so here this is the base condition, so I will be returning one here. Okay, so uh, okay, I have reached four here, right? So from four you need to return one, right? So you have written one. So you will from one step I have reached one. Only in one way I can reach the top. Okay, so from here I got the solution from reaching one step. Okay, if I go two steps further, I'll be reaching five, which is an impossible way, right? So from here I'll be returning zero here. So from here I'll be returning there's some, right? So one will be the answer. So if I go again here, so from here I need to go two steps further, right? So initially I'll be going to the top, so I'll be returning one here. Okay, so I'll return one here. Okay, after this I'll be, what should I do? um, I'll be returning the sum of these two ways, right? So I'll be returning two here. Okay, so from here, from one I've reached one. If I go one step further, then I'll be going with two steps, right? So if what if I go two steps further? So I'll go two steps further. Okay, so I have reached three here. Okay, so if you observe, for reaching three, you have already calculated the answer here. So where you have calculated, it is calculated here, right? So this is a dynamic programming here. Okay, uh, you have you are going to the position where it is already calculated. You're you are calculating the solution. You are calculating solution. You are calculating the solution for the position where you have already reached. So redundancy is happening here. So to avoid redundancy in programming, dynamic programming comes into play. Okay, so they have already calculated this answer for here. So if you try to store this answer in some other variable, like if you try to store this answer, then uh, you can directly return that answer whenever you have reached that position. Okay, so this is dynamic programming here. So this is the main step of dynamic programming. So the dynamic programming helps in redundancy, like you have helps in not doing the problem one more time. Okay, not doing the same problem uh, at a time, like not uh, repeating the same problem, not repeating the same problem, not calculating the same problem. Okay, one more time. Okay, so if you have solved the problem for a subproblem, then you have to store that subproblem answer in some variable. And if at all the subproblem again comes into your way, then you can directly return that subproblem from that position only. Okay, so how? time complexity is being reduced here. See, so see now. So my subproblem is already calculated here. So my from my subproblem I've got an answer called one. Okay, so from here I can just return one here instead of instead of going to another position, uh, like uh, like further more, like one step and two steps more. Directly I can return one here. So if I calculated the answer and stored the answer previously, okay, so I have calculated the answer and stored the answer previously, right? So I'll be returning the answer directly here. So this step will be not happening for me. Okay. So this step will be not happening for me. Okay. This calculation of this step will be not happening. Okay. So from here I'll be returning just the summation of these two. So this is a beautiful tree here. Like if you observe here. So again, so from here you have reached one position, right? So you will be going two steps further, right? So you will be going to a position where you have calculated the answer previously again. So where you have calculated the answer previously? So here, right? This subtree is already calculated, right? This subtree is the and this subtree is same. I have already calculated the answer for this subtree. So why you need to again calculate the answer for that subtree again? So uh, instead of that, you might have stored this answer in some another variable, and directly when that sub problem comes, you can just return it, right? This is a beautiful approach of dynamic programming here. So I have already calculated my answer for this previous problem, so I'll just return that answer instead of calculating this subtree. Okay, instead of calculating this subtree, I'll just return this. So what is the overall tree I have calculated here? This is the overall tree I have calculated. Okay, so 0 1 2 3 4, this is the overall tree I have calculated. This is the tree I have not calculated in the dynamic programming approach. Okay, so the time complexity will be what? So I have reached only the n steps, right? So one step, one step, one step, and one step. Instead of going to 2 to the power of 2 to the power of n. So into exponential time complexity, I have reduced the exponential time complexity to big O of n time complexity. If you observe here, so instead of using exponential time complexity here, I have reduced the time complexity to big O of n time complexity by using dynamic programming. Okay. Okay, you have understood the, I hope you have understood this dynamic programming. If you haven't understood this dynamic programming and you want a clear explanation of dynamic programming, you can just comment down. I'll be uh, again explaining you this dynamic programming approach. Okay, and if you want more these kind of problems to enhance the dynamic programming and to master the recursion, please let me know in the comment section. So I'll be doing an variety number of problems in from recursion and dp. Okay, so this is the whole approach of the dynamic programming. The main motive of the dynamic programming was to decrease the time complexity. So this is the dynamic programming approach. So we will try to now apply dynamic programming. How to apply dynamic programming? So as I said, we need to have, I will use a variable. I said right in here I said right. So if at all we have stored this answer in somewhere, then there is no need of calculating this subtree again, right? So now I will calculate now I will try to store the answer in a try to store the answer so that I can, whenever I reach that position again, then I can return the answer simultaneously. Okay, so I will try to store the answer in a dp array, and I will pass the dp. Okay, so this will be the dp. So what will be my dp? Initially my dp will be 0, right? So if dp of I not equal to 0, then I have calculated the answer previously, right? So if my dp of I is not equal to 0, then uh, it is some other answer. So it means that I have calculated an answer for that subtree previously, right? So I can just return tu rn dp of I. So instead of directly returning this answer, first I will try to store in a variable. That is, for ith position, uh, I'll be from ith position to reaching the top. I'll be using these many steps to reach these many distinct ways to reach the position. Okay, so this answer can I'll be storing in that dp of I. Okay, so at ith position, for example, uh, for for example, for create from third position to reach the top, uh, I'll be using one distinct way to reach the top, right? This number of distinct ways can be stored in a DP of file. Okay, so the state of the DP will be storing the number of ways. Okay, number of distinct ways from a position. Okay, so in this way, I can solve this problem. Okay, so just simple, right? By just modifying the recursion. Okay, uh, storing the position number of distinct ways in a DP, and whenever the position has has number of distinct ways not equal to 0, then I have already calculated, then I can say that I have already calculated the number of distinct ways from that position, so I can directly return that position from here instead of calculating this all things here. Directly I can return from here. So if at all I haven't reached the position, then I will calculate for them, and I will be returning the number of distinct ways from that position. Okay, so if we try to run this position. Okay, so I need to return dp from here also, right? Okay, okay, it has successfully submitted, and when I try to submit, okay, the problem is solved. So this is the recursive approach and the DP approach. Here, the DP approach is a top-down approach. If you want the tabulation and the this is the memorization approach. If you want a tabulation and the optimal solution of this problem, then please let me know in the comments. I'll be posting you the answers. Okay, so this is the solution here, and thank you.